Okay, so in this video we will be talking about the the meaning of basically basis, and then we'll be talking about the span of a vector space. But before that we have to know some basics, like suppose I have a vector space S equals to v1, v2, v3 dot dot dot. We have some number of vectors. If S belongs to R2, if S belongs to, it's not actually S, it is basically if V belongs to R2, then this vector space, it basically means if this is the y-axis, this is the x-axis, so we are having that V is like here somewhere, so it is a coordinate on the xy plane, on a two-dimensional plane. So this V can be written as V, suppose 1 comma 2. So this is suppose V1. So it is 1 here and 2 this side. So this is the meaning of a vector in a vector space. A vector, if it was three-dimensional, if belongs to R3, then the V would have been on, there would have been another Z axis there. So then it would be three-dimensional. Above three-dimensional, we don't have the provision of visualizing them. So we can only visualize up to three dimensionals. But the vectors can actually move till n dimensionals. Now, we know there is something known as the primary colors, and the primary colors are respectively red, then we have a primary color as green, and we have another primary color as blue. Now it's red, green, and blue. It's not red, blue, and yellow. Many people make it a mistake. It's red, green, and blue as the primary colors. And we know one thing, that by mixing these three primary colors, we can create any number of colors or any colors in the world in the digital plane, of course. So it's the RGB. Now we are having, suppose, a line. So these are basically any color, suppose, equals to some amount of red plus some amount of blue plus some amount of green. And why we are doing this, I will just come to that in a while. So suppose we have a real line that looks like this, and there is only one on the real line. So we are only taking the number one from the real line. This is the line of real numbers. This plus infinity and this is minus infinity. And so with one, can we create all other values by doing some scalar operations? So we can actually do. So with 1, if we multiply 1 with any scalar alpha, we can get alpha. So if we want a value, suppose 2.435, we can take alpha equals to 2.435 and we can just multiply it with 1 and we can get 2.435, and that belongs to this real line. Similarly, we can take any value of alpha and we can actually operate on that with the number 1 on the number line, and we can get any number on this real number line from minus infinity to plus infinity. So 1 can be called something here. We will look into that a little later. Similarly, if we are having a 2D plane, so let's draw the coordinates. We are having this plane 2D and we are taking two vectors. We are taking the vector, suppose, let's change the color of the ink and we can do it in this ink. So we can do it like vector 0 comma 1 is here and vector 1 comma 0 is here. 0, or should we write it like 1 and 0? Now imagine that we want a point, any point on this number line, on this coordinate space actually, on R2. If we want any point, suppose in this R2 we want a point like 5 and 3. We want this point. 5 and 3 means somewhere around, this is 5 and this is somewhere around 3. So basically we want this vector. This is 5 and 3. So what will we do it like? So we can actually perform an operation like there can be an alpha into 0 comma 1, and there will be another beta into 1 comma 0 to get the value 5 and 3. So we can tell it like, we can take alpha to be 3 and beta to be 5 here. So alpha is 3 and so 0 and 1, plus we take beta to be 5, so that becomes 1 and 0 here. So it becomes 5 and here it's becomes 0 3 and it becomes 5 0. So we are getting 5 comma 3, this vector. And like that we can take any arbitrary value of alpha and beta and we can plot, or we can actually get any point on the 2D space with just these two vectors 1 0 and 0 1. Similarly, in three-dimensional plane also, if we take three vectors, so in 3D plane or in the R3D space, if we take any three vectors which are like 1 0 0, 0 1 0 and 0 0 1, and we operate it with scalar values like alpha, beta and gamma, so we can get any number of values or any coordinate on the R3 plane, any vector on the R3 plane with just these three vectors. So we can infer one thing, that there is always a minimum number of vectors which can be used to obtain or to deduce all the vectors in that specific vector space. And that thing is called the basis of a vector space. So basis of R1 or simply R is 1, because with 1 we can actually do any, we can actually have any number on the R1 space. With basis of R2 can be like 1 0 and 0 1. So with 1 0 and with 0 1, we can actually get or deduce any vector on the R2 plane. Basis of R3 can be written as 1 0 0 0 1 0 0 0 1. And this, with these three vectors we can actually obtain any vector on this R3's vector space. So this is called the basis of a vector space. The basis of a vector space is the minimum vectors which we can take to have the entire vector space by just performing some operations on them. Now we have to understand one thing, that if you look carefully, we are having, for R1 we are having number of terms in the basis is 1. For basis of R2 we are having number of terms in here is 2. For basis in R3 we are having number of elements here as 3. So basically this is a theorem that the number of elements in the basis set of Rn is always equals to n. But this is not This does not mean actually that they are unique. So we have to understand that the number of elements in the basis set of a specific vector space is always unique, that is Rn, but it's always unique, that is n, but the basis can be different. For example, suppose if we take for R2 case, we told that the basis here is 1 0 or 0 1. What if we have a basis, we select a basis like uh, we can call it like 1 1 and 1 0. Now this can be also a basis. If you take any point, like if we take a point to be, let's take some arbitrary negative points. So -2 comma -4, suppose we want to obtain this point from these two. So if we wanted to obtain from here, then we would have done -2 into 1 and 0 plus -4 into 0 comma 1. But how to obtain this from here? So we can actually, what we can do is we can have -2 we are trying to do. So what we can do here is some alpha into 1 1 plus some beta into 1 0 becomes -2 and 4, -4. So if we see it like alpha plus beta is -2 and alpha equals to -4, so we can basically see if beta equals, so alpha is -4, so beta will be 2. And now you just put them and you see if alpha is -4 into 1 1 plus 2 into 1 0, it becomes, so -4 into is -4 and here is 2 is -2, and -4 here is -4 plus 0 is -4, so you are getting the same vector. So this can also be a basis for R2. So the basis set of a vector space is not unique, but the number of elements of the of a vector space is always unique, and that equals to n for the Rn vector space. Now, what do we exactly mean by the term span? So the span of a vectors of the basis is actually the elements or the vector space which can be obtained from that specific basis which we are having. So with 1 0 and 0 1, so the span of, basically we should write it like this. Let's remove this also. So span of 1 0 and 0 1 is R2. Basically we can find all the elements on the R2 vector space with just these two vectors. So the span of these two vectors is R2. Similarly, for the span of 1 1 and 1 0 is also R2, because we can obtain any vector or any vector on the vector space R2 by just using these two vectors from that specific vector space. So this is the meaning of span of a vector space. Now there is an important thing to notice, that suppose we take the basis of a vector space like 1 0 0 1 and 1 1. Now you'll notice something interesting here, that is 1 0 and 0 1 are the two vectors which cannot be obtained from any other vector. But if you see 1 1 here, this 1 1 can be written as 1 into 1 0 plus 1 into 0 1. That becomes 1 1. So basically this 1 1 here can be called as a redundant vector. And redundant vectors are always removed from the basis set. So the basis set is basically the minimum vector number of vectors with the vectors itself, which can be used to obtain the vector space. So there should not be any redundant vectors there. So that is the meaning of a basis set. And also you will notice, so this is an important phenomena and it is known to be linear dependence, because we can see one thing here, that 1 1 can be written as some linear function of 1 0 and 0 1, basically some alpha into 1 0 plus some beta into 0 1, where alpha and beta belongs to scalars. So this is a linear dependence on 1 0 or 0 1, or we can also tell it like 1 1 is linearly dependent on 1 0 and 0 1. So linearly dependent vector should not be a part of the vector space, or should not be a part of the basis of a vector space. So what should be a definition of linearly independent? So linear independence means that if you have vectors v1, v2, dot 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 vn, these vectors are called to be linearly independent if there exist only there exists alpha 1 comma alpha 2 comma dot 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 alpha n, all of them equals to 0, and such that alpha 1 v1 plus alpha 2 v2 plus dot 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 plus alpha n vn equals to 0. And this can only happen when alpha 1, alpha 2, comma dot 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 alpha n are all zeros. Except that it can never happen. So when alpha 1, alpha 2, dot 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 alpha n are all zeros, this condition is called the trivial solution, or the trivial condition. Only when all of them are the trivial condition, then we can tell them, and it becomes 0, we can tell the vectors are linearly independent. Or if there exists any other solution to this equation, alpha 1 v1 plus alpha 2 v2 plus dot 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 alpha n vn equals to 0, then that vectors are known to be linearly dependent. A basis of a vector space can never have vectors which are linearly dependent. They have to be linearly independent. And the last very important point is the choice of basis of a vector space is not unique. We can choose any basis we like as long as they are linearly independent. For that matter, if we find any two vectors, suppose we find any two vectors which are linearly independent, can become the basis of R2. So we were having like 1 1 and 1 0. We can also have like, suppose we are having minus 1 0, and we are having another which is 0 and 2. This can also become a basis of the vector space R2. And you can also try this at home by taking some arbitrary vector and trying to find that arbitrary vector by some operation on these two vectors, and you will be able to find, for example, if we try to find like 5 and 7, so we can actually find it from there. We can actually do is minus alpha into and 0 plus 0 and 2 beta equals to 5 and 7. So we get to know that alpha equals to minus 5 and beta equals to 3.5. And if you actually do the thing, you will notice that minus 5 into minus 1 0 plus 3.5 into 0 comma 2 is actually 5 comma 7. So this can also be called as a basis for R2. So the choice of basis of a vector space is not unique, but the number of elements in the vectors in the basis of a vector space is always unique. Notice how here and in the last example and in the previous example for R2 we the basis set only had two elements, and it is bound to have two elements. It can't have more than two elements, because if it has more than two elements then there will be a linear dependence coming in the set, and that is not valid. So the number of elements in the basis of a vector space is always unique. And the span, as we told, the span is all the vectors which we can obtain from that specific vector space or vector set of the basis can be known as the span. So for this is R2. For if we take three linearly independent vectors, then it is R3. The span would become R3 and so on. So that's all about this video. We'll meet in the next one.